Hello my friends, and welcome back to the You Can Do TV channel. Steel pipes over several meters long are precisely straightened and cut with Bausteel's multi-roll straightening and plasma machines. Each seamless steel pipe receives careful inspection using a probe to confirm an unobstructed internal channel. The pipe ends are manually adjusted along the axis, ensuring no metal shavings or oxide scales remain inside. Following inspection, the steel pipe straightening machine is engaged, employing multi-roll rolling and pressure correction mechanisms to bring the pipe into exact geometric alignment. Cutting operations come next, with sawing and plasma machines producing pipe ends that are flat, burr-free, and precisely sized. Never expected such consistency across these heavy-duty pipes. Heat treatment furnaces then anneal or normalize the pipes according to strict temperature, timing, and cooling protocols, enhancing structural integrity and mechanical performance. Finally, acid washing removes surface oxides, rust, and impurities, leaving smooth, clean pipes ready for further manufacturing stages. The combination of human oversight and advanced machinery at Bausteel ensures every pipe meets rigorous quality standards, highlighting the skill and coordination required in modern steel production. This workflow really emphasizes the engineering mastery behind every pipe. At the steel plant, threaded bars move in perfect synchronization, each precisely cut to the required length by a high-speed flying shear machine. The accuracy of every cut exceeds expectations, ensuring uniformity across the entire batch. After cutting, the bars travel smoothly along chain or roller conveyors toward the automatic binding station. Here, photoelectric sensors and PLC control systems align each bar for accurate stacking, forming compact bundles weighing between 2 and 3 tons. Hydraulic or pneumatic tensioning devices secure the bundles with high-strength steel wire or durable polyester straps, their joints fastened by hot melt welding or mechanical buckles. Once binding is complete, an electromagnetic crane lifts the heavy bundles with remarkable stability, as if they were weightless. The finished products are then neatly arranged in storage areas or directly transferred to the loading zone, ready for shipment, reflecting the plant's precision, efficiency, and technological sophistication. Wire rods are produced by hot rolling steel billets in high-speed continuous rolling mills. The process begins when square steel billets are heated in a reheating furnace to around 100 to 200 degrees Celsius, making them soft and malleable. The heated billets are then passed through a series of rolling stands that gradually reduce their cross-section while increasing their length and speed. As the billets are transformed into long, thin strands, precision control systems ensure consistent diameter and surface quality. The final rolling stage shapes the material into wire rods of the desired size, usually between 5.5 and 16 millimeters in diameter. After rolling, the wire rods are rapidly cooled on a controlled cooling conveyor to obtain the required metallurgical properties and mechanical strength. The cooled wire rods are then coiled into compact bundles, typically weighing 2 tons, and tied securely for storage or shipment. These wire rods are used as raw materials for producing various products, such as steel wires, nails, screws, springs, and welding electrodes. The continuous rolling process ensures uniform quality, high productivity, and excellent dimensional accuracy. Red-hot steel is heavy and rigid, yet machines and hands manipulate it smoothly. At Stahlwerk Georgs Marienhut, steel transforms under controlled conditions into high-quality products. Raw steel is first guided through preheating furnaces to reach an optimal temperature. Conveyors move each piece precisely into rolling mills. Operators monitor gauges and adjust rollers to shape steel into sheets, beams, or coils. The coordination between human oversight and machine movement is impressive to follow. Once the initial rolling is done, automated presses and leveling machines refine dimensions. Small tweaks here determine structural integrity in construction. Finished pieces pass through inspection stations, where straightness, thickness, and surface quality are verified. You might not expect so many checks for something that looks simple at first. Steel components then move to cooling lines, maintaining consistent strength and preventing warping. Feels satisfying to see metal behave exactly as intended after all this effort. After cooling, the steel often passes through multi-stand rolling mills, where several sets of rollers progressively smooth and shape it into bars, rods, or tubes. This step ensures precise dimensions and a refined surface, preparing the steel for specialized applications. The process combines industrial power with skilled oversight, producing steel that will withstand heavy loads, extreme environments, and demanding applications. Follow slabs as they travel through AHMSA's continuous casting machines, forming precise dimensions. At Altos Hornos de Mexico, the iron ore is first processed through pelletizing and sintering, while metallurgical coal undergoes coking. The iron arrives at the pellet plant as slurry via a 300 km viaduct. After filtration, the recovered water is returned, and dry iron is sent to balling discs to form small spheres called pellets. These pellets are baked at 1,300 degrees Celsius to reach the hardness needed for the blast furnaces. Meanwhile, metallurgical coal is treated in vertical brick-lined ovens for 18 hours, producing coke that fuels the blast furnace process. Byproducts like coke gas are captured for later use. You can really appreciate the scale of these early steps. In the blast furnace, layers of pellets, sinter, coke, limestone, and dolomite are deposited in precise quantities. Hot air injected from the base ignites the coke and melts the iron at temperatures up to 1,650 degrees Celsius. The resulting molten pig iron flows into 200-ton ladles via channels called piqueras. Sulfur content is reduced in the desulfurization plant using calcium and magnesium carbides. Slag is collected and cooled with water before being stored or sold as a by-product. Conversion to steel uses the BOF process. Scrap is loaded into 150-ton pear-shaped converters lined with refractory bricks. Oxygen, argon, and nitrogen are injected through lances above and below the converter. After 45 minutes, molten steel is obtained and adjusted with ferroalloys for chemical composition. Secondary metallurgy treatments ensure product quality. The continuous casting machines transform the molten steel into billets, which are then cut to required dimensions. The precision achieved here really sets the foundation for all downstream products. Hot rolling begins with reheating billets to 1,330 degrees Celsius. Plate mills reduce them through multiple reversible passes to desired thicknesses, followed by cooling, straightening, and cutting. Strip lines process billets into hot rolled coils, reduced down to 1 inch or less depending on customer specifications. The green coil system prepares them for delivery or cold rolling. Cold rolling further reduces thickness and enhances physical properties. Annealing furnaces heat the strips to 750 degrees Celsius for controlled softening. Temper mills provide specific hardness, while skin pass and tension leveling lines improve surface quality and uniformity. Finally, heavy structural profiles are made by reheating square blocks called tochos to over 1,250 degrees Celsius, passing them through rolling trains to produce beams, channels, and angles for construction. Industrial gases, energy, water, transportation, and maintenance workshops support the entire production chain. You rarely see such a complete integration of technology and human expertise. Altos Hornos de Mexico ensures quality with strict national and international standards applied by highly trained technicians and workers. How does SINOM Group Company Limited achieve simultaneous rolling, cutting, and cooling at high speeds? The incoming billets are separated into 2, 3, or 4 strands and guided through finishing mill stands, where rolling, cutting, and cooling happen simultaneously. How efficiently each strand is processed at speeds up to 20 meters per second. The walking beam cooling bed and automatic bundler ensure bars maintain quality and uniformity. Operators monitor the vertical, sectional, combined reducer, and rotary flying shear for smooth operation. Watching such coordinated systems run makes you appreciate the engineering involved. The line is highly automated, yet allows simple operation and maintenance. Entry roller tables feed strands seamlessly onto the cooling bed, while bar counting and separation systems keep production precise. High rigidity, short stress path rolling ensures minimal deformation, producing construction and alloy steel bars ready for shipment worldwide. Seamless pipes offer unmatched strength with no welds, ideal for structural applications. The production line uses a combination of piercing machines, automatic tube rolling machines, reeling machines, sizing machines, and reducing machines to handle each step. The precision in rolling and piercing ensures the steel achieves the proper diameter and wall thickness consistently. Heated billets are first perforated with a piercing machine to create the tube embryo. The diagonal rolling method, also called the Mannesmann method, extends the tube rapidly while maintaining material integrity. Each pipe then undergoes sizing or reducing to achieve exact dimensions before cooling. Straightening machines correct any minor bends, and water pressure tests detect cracks to ensure quality. Every step is controlled to meet engineering standards for durability and reliability. Marking finalizes identification before the pipes are warehoused. The expertise of the SMG technical team ensures seamless integration of machines and processes, highlighting the engineering behind each pipe. Notice the steel bending progressively under measured hydraulic pressure, creating perfect curves. Steel plates arrive at the hydraulic forming station, each measured and aligned for accuracy. The teamwork here is remarkable. Operators guide heavy plates with care, while the machine prepares for action. The forming press applies immense hydraulic pressure to bend the plate into a precise dish and shape. The engineering choices in pressure control show deep attention to material behavior. Watching the plate deform under force shows engineering at its finest. Sensors monitor pressure and alignment, ensuring each part meets exact specifications. Plates are lifted and repositioned for subsequent forming operations if needed. Even seasoned engineers admire the consistency achieved in every piece. Quality control at this stage prevents small deviations from affecting the final product. Seeing steel transform under hydraulic pressure like this is surprisingly satisfying. Each step reflects careful planning, mechanical precision, and safety consciousness. The layout of the station maximizes operator efficiency while minimizing risks. Repeated cycles show how durability and speed can coexist in industrial forming. Such a system makes large-scale, high-quality production possible with minimal waste. The discipline in handling each plate ensures repeatability and reliability across batches. Wencherminatan. Thousands of tons of rebar are measured and processed daily at Lloyd Rebar for nationwide projects. Steel rebar is carefully cut and bent to precise lengths and shapes to reinforce concrete in buildings nationwide. Each job is measured multiple times to ensure exact compliance with customer specifications. Rebar comes in various sizes and bends, adjusted based on engineers' requirements for each structure. The team consistently reviews specifications before each operation to maintain high-quality standards. Operators run advanced machinery, including the shilt, which can cut rebar down to millimeter accuracy. Each piece is checked, straightened, and shaped before being sent to the construction site. Every adjustment and inspection contributes directly to the durability and safety of the structures these bars support. Seeing this coordination in action really emphasizes the engineering behind everyday structures. NN. What allows American Steel to handle massive, complex steel projects with such efficiency? Track welders, plasma tables, and punch drill lines efficiently shape beams and plates. Engineers utilize SDS2 3D modeling software to link design with production seamlessly. The speed at which these complex structures assemble is incredible. iPads integrated on the shop floor ensure precise guidance. Hard to believe such large-scale fabrication is handled with compact, high-tech tools. The result: durable steel structures shipped across the globe. NN. Kiernan Structural Steel Limited, KSSL, located in Longford, Ireland, is a leading manufacturer of high-quality structural steel components. The company utilizes advanced technology and skilled craftsmanship to produce precision-engineered steel products for various construction projects. Steel plates are thoroughly cut using state-of-the-art CNC plasma cutting machines. These machines utilize a high-temperature plasma torch to cut through thick steel plates with remarkable precision. Operators ensure each plate is correctly positioned before the cut, minimizing errors and waste. Following the cutting process, KSSL employs large multi-spindle drilling machines to efficiently handle bulk hole drilling. These machines are capable of drilling multiple holes simultaneously, significantly increasing throughput without compromising quality. Industrial robotic arms perform automated welding along structural components. These robots move along metal sections, joining them with consistent seam quality. This automation reduces human exposure to heat and sparks, enhancing safety and efficiency. Automation integrates cutting, drilling, and welding seamlessly. The factory demonstrates how modern steel production blends advanced machinery with skilled supervision to achieve both efficiency and precision. NN. Never expected shaping a shovel to demand this much heat and force. At Tiruchi Agro Industries in Dindigul, Tamil Nadu, artisans transform raw steel into the mammoth shovel blade. Steel billets are selected for strength and heated in industrial furnaces until malleable. Each heated billet is clamped. Operators adjust the blade carefully, guiding each strike to form the basic shape. The force of the machine is relentless, yet each movement is finely controlled. You can almost feel the power behind each strike. Each tap is both correction and celebration of skill. Even small adjustments here define the tool's future efficiency. After the machine sets the rough profile, artisans pick up hammers to refine the blade manually. Every tap corrects curves, sharpens edges, and balances thickness. The hand hammering adds a rhythm the machine can't replicate. Feels like the blade comes alive under every hand strike. How much shape a few taps can perfect. The contrast between molten heat and cooled steel is striking. You can imagine the countless shovels crafted this way over decades. Each spark from hammering hints at the effort invested. The steel bends to both fire and skill in equal measure. The interplay between machine and hand is surprisingly elegant. Even subtle corrections change the digging performance dramatically. You might not expect manual taps to impact a massive piece of steel this way. Every strike leaves a signature of the artisan's care. The end result is a perfect balance of human touch and mechanical strength. The dedication is tangible even before the blade is finished. Once the shape is precise, blades are moved to grinding stations. Each blade is a product of fire, force, and careful craftsmanship, prepared for eventual assembly with handles. Powell Valves, Yancheng plant in Jiangsu province, produces industrial valves with unmatched quality and advanced engineering. Spanning over 400,000 square feet, the facility integrates machining, assembly, and testing under one roof. Each raw material batch undergoes rigorous inspection with X-ray and gamma-ray equipment to ensure compliance with Powell's strict specifications. The valves are fabricated using CNC vertical and horizontal machining centers, lathes, boring, and drilling machines capable of handling large diameters with precision. Material testing includes hardness, impact, tensile strength, chemical analysis, dye penetrant, and ultrasonic detection. Valve components are machined to tolerances as tight as 0.01 inches to ensure proper sealing. Assembly technicians carefully assemble, test, and pack each valve following detailed procedures aligned with API 598 and other customer-specific requirements. Cryogenic valves are tested to -320 degrees Fahrenheit, ensuring performance in extreme conditions. Powell's engineers use AutoCAD and SolidWorks to design, simulate, and analyze each product, minimizing errors from design to manufacturing. End valves include gate, globe, check, butterfly, bellows, cryogenic, and specialty types with sizes from 1/2 to 60 inches and pressure classes up to 4,500. Strict multi-stage quality control ensures valves perform reliably in petrochemical, power, LNG, and other industrial applications. The combination of skilled engineers, advanced CNC machinery, and precise testing guarantees industry-leading performance. Powell's commitment to material verification and thorough testing underlines why they remain a trusted global partner. See how each hydraulic press molds steel into perfectly round rims at Vlucon. The production begins by cutting steel blanks to precise dimensions, ensuring every rim will meet tight specifications. Can't believe how neatly each sheet fits into the next stage. Once cut, the steel moves to the pressing station. Using hydraulic presses, the metal is formed into circular rims, with controlled force shaping each contour perfectly. Even the small curves are handled without a single wrinkle, which is impressive for such thin steel. For rims that require special features, additional punches and dies create holes and slots accurately, aligning with the intended design. The next stage involves heat treatment, which strengthens the rims for durability and stress resistance. Temperature-controlled ovens ensure that the steel gains uniform hardness across the entire surface. After cooling, each rim is inspected for shape consistency and defects. The way each rim holds its exact roundness is almost unexpected. For finishing, surfaces may be coated or polished depending on the order, enhancing corrosion resistance and visual quality. Automated systems help maintain repeatable precision, while operators monitor and adjust for minor variations. It's kind of surprising how the combination of machine efficiency and human oversight produces flawless rims so consistently. Finally, the rims are packaged in protective cases, ready for delivery. Small batches allow customization, which gives Vlucon the flexibility to meet specific customer requirements without losing efficiency. Throughout the plant, equipment like presses, punches, and ovens integrate seamlessly with human operators, showing a refined balance of technology and expertise. Every stage of the process is carefully designed to ensure high-quality pressed steel rims, from raw steel sheets to the final product, ready to meet performance demands. Lot N UZ. Every concrete sleeper that supports a train's weight starts life inside a fully automated line like this one, where Overrail turns raw materials into rail foundations that endure decades of service. Reinforcement preparation marks the opening phase, with steel bars assembled and tied to form the sleeper's strong skeleton. Mold oiling follows to ensure smooth release once curing is done. Then, mold preparation readies each frame for the coming pour. Alignment and cleanliness are crucial. The attention to mold integrity directly defines the sleeper's dimensional accuracy later in service. Reinforcement positioning locks the steel inside molds before the stressing system applies tension, a pre-tension setup that boosts sleeper strength. This step alone decides the sleeper's long-term durability. Concrete production comes next. Aggregates, cement, and water blend in automated mixers before moving to casting. During sleeper casting, concrete flows evenly through the molds, ensuring density and stability. Steam curing takes over, hardening each sleeper in heat-controlled chambers. After the curing cycle, the realizing phase releases internal tension, readying the sleepers for demolding. That subtle release moment truly shows how mechanical precision keeps the structure intact. Testing and quality control follow. Compression and bending tests confirm each piece meets strict standards. Nothing leaves this line without proof of strength. Fastening systems are installed, then sealed for durability against weather and vibration. Sleepers are stacked and stored in neat rows, awaiting shipment across Europe's expanding rail network. Seeing thousands of them lined up feels almost futuristic. Overrail's process captures industrial efficiency at its purest, structured, smart, and built to last. Automation here doesn't just save time, it ensures that human precision and digital control move as one. Heat and distance define this monumental build, 416 kilometers of rail stretching across Abu Dhabi's desert, connecting Shah to the port of Ruwais. In this vast expanse where temperatures reach 50 degrees Celsius, teams and machines work in sync to make the UAE's first freight railway a reality. That scale alone already says everything about ambition. Work opens with rail delivery and handling. Prime rails are loaded, moved, and positioned with cranes before flash butt welding units form long continuous lengths. Each joint is tested to ensure flawless conductivity and strength. There's something striking about how those glowing seams turn into one seamless line of steel. Operators conduct detailed inspections, maintaining alignment through GPS-based topographic surveys that guarantee perfect rail geometry. Next comes the base. The first ballast layer spreads beneath sleepers, locking them firmly into position. The MCB-01 track-laying train follows, capable of producing up to 2 kilometers of new track per day. Rails and sleepers are set, fastenings secured, then released again for fine adjustments. It's wild to realize how efficiently such massive sections fall into place, with mechanical rhythm. Further welding and grinding refine the joins until the rail surface is smooth and unified. Ballast filling and tamping stabilize the foundation before a second layer is profiled for exact level and alignment. Track stabilization applies dynamic stress equivalent to the passage of 50,000 tons, proof that each section can bear real-world load from day one. The engineering foresight here feels almost unreal. Maintenance teams then brush, vacuum, and clean the track to remove sand and debris. Rails are de-stressed, cut, and fitted with pullers before aluminothermic welding finishes the line. Quality control seals every section with on-site safety checks. CRO management oversees safe operations during all movement on and around the infrastructure. Shunters handle turnout zones, and every worker adheres to a zero-accident philosophy through continuous safety training. You can sense the discipline that defines every part of this operation. The outcome: 265 kilometers of single and double track, forming 419 kilometers total. Abu Dhabi's first railway line is not just built, it's engineered for endurance and speed across generations. Hard not to feel awe for what persistence and coordination can achieve in the desert. "1,200 U-shaped beams rise from a vast construction base in Jimo, forming the foundation of a 58.4-kilometer railway line built by CRCC. Each beam is born from tons of reinforced concrete shaped and set across 20 casting platforms. Steel reinforcement is tied at 10 preparation stations before concrete from 2 HZ90 batching plants fills the molds. The precision and timing between crews here feel like pure coordination under pressure. Once cured, the beams are lifted onto transport vehicles and moved to one of 285 storage bays for inspection. Cranes glide over the yard, loading each segment with practiced ease. Hard to imagine how many calculations go into lifting a single piece this size. At the installation site, massive cranes align every U-beam on concrete pillars, connecting them with bolts and tension cables. Operators monitor every move, while ground teams lock the pieces in place to create seamless spans. Safety and quality management run side by side. CRCC enforces its one network, four grids approach, covering design, operation, supervision, and emergency control. Workers undergo training, testing, and inspection before every new stage. The discipline here shows how infrastructure can be both human-driven and machine-perfect. Each beam adds another step toward a railway built for endurance and speed. Didn't expect construction on this scale to move that smoothly. Lifting a 150 meters turnout section in fewer than 5 hours highlights how the PEMLM system transforms track works. On the LGV Bretagne Pays de la Loire line, a 150 meters long turnout splits in 2 sections and only 3 operators, 16 PEM gantries, and 14 LEM trolleys coordinate the installation. First, the auxiliary runway is installed, and the PEM inclinometers automatically level the turnout. Next, the LEM trolleys transport the second section while the PEMs handle the first. Slewing is precisely controlled to ensure perfect positioning of the turnout and rails. This integration of gantries and trolleys reduces on-track time dramatically. Once installed, the track system is ready for immediate traffic. Speed of up to 6 km per hour under full load is achieved by the LEM when transporting equipment. Efficient mechanics and minimal staff underscore how modern track laying can evolve. The runway gets removed and the site clears fast for operations. Seeing such a complex turnout laid so quickly brings a new benchmark in rail infrastructure. Heat sparks the unseen power in aluminum, the key element in this specialized rail welding reaction. Operators rely on aluminum's high exothermic energy to bond steel rails efficiently and durably. The sequence opens with precise aluminum powder measurement, ensuring the chemical mix is exact. Flux is added next to clean the metal surfaces and promote uniform welding. Timing is crucial. The slightest delay can affect joint strength. Ignition follows, triggering an intense thermite reaction that melts the contact points. The molten aluminum flows into the joint, fusing the rail ends seamlessly. Once cooled, the welded joint is ground and inspected. Tests confirm the bond can handle extreme train loads. Seeing the sparks fly and the joint form in seconds is quite a rush. The finished weld ensures decades of rail service without failure. The chemical reaction here is a small-scale powerhouse for rail infrastructure. N Vormity 10. "250 kilometers of track renovated, trains running at full capacity with reduced downtime." On the Courageous Railway, every meter of renovated track represents a commitment to efficiency. Pelicano Construcos tackled this challenge, with full-scale renovation underway. How much planning goes into keeping a railway line fully operational while being rebuilt? Crews first remove old rails and ties systematically, ensuring each section is ready for installation. Surveying teams mark each section with precise measurements, guiding crews and machines in synchrony. The alignment work is paying off. Trains will glide smoother than ever. Ballast is redistributed and compacted carefully to create a stable base for the new track. The track bed is reinforced and leveled, ensuring that rails lay perfectly without future settlement issues. Specialized machinery applies geometric corrections, including 9 advanced ballast tamping units, making high-capacity operation possible. Rails are replaced or adjusted in carefully calculated sequences, reducing downtime and allowing trains to run at full capacity. Fastening systems are checked, and ties are aligned with tight tolerances. Each welding and joint adjustment is verified to maintain consistent rail integrity. Maintenance cycles are shortened through this precision, which minimizes long-term operational disruption. Continuous monitoring during installation ensures deviations are corrected immediately. The renovation strategy emphasizes efficiency, combining human expertise with technology to maximize safety and throughput. By the project's completion, 250 kilometers of the Carajás Railway are fully renovated, supporting maximum traffic volume and reducing stop train hours. Pelicano's investment in innovative technology ensures that each rail segment meets the highest standards of safety and reliability. Bent axles and wheel hubs that once required manual adjustment now fit automatically. Precision robots guide the axle into the automated cell, aligning wheel seats to micron accuracy. Then the assembly moves to the final measurement station to verify dimensions and ensure safe operation. Only 2 operators monitor this line while the cell produces a complete wheel set every 3 minutes. The automation makes heavy rail manufacturing feel streamlined and efficient. Watch how massive components meet such tight tolerances. Every train's smooth ride depends on what happens here, where worn wheel sets regain their perfect geometry under the Danobat DPL's control. Wheel sets are clamped and scanned to define machining strategy, extending service life. Dual heads cut both wheels at once, optimizing balance and speed. That synchronization between axes feels like pure engineering rhythm. Adaptive control adjusts every movement, protecting the machine while keeping output high. Internal faces and brake discs are then machined in sequence, followed by final measuring for validation. Seeing how automation keeps each cut perfectly aligned is just brilliant. Finally, wheel sets unload automatically for inspection. AHMSA. Rising above the Italian plains, the VI-10 viaduct links 2 key sections of the Verona-Padua high-speed line, a 765-meter bridge that stands as proof of modern rail engineering. Every pier, beam, and abutment here speaks to the balance between structural power and design precision. Hard to imagine how each segment fits so seamlessly across such distance. Foundation work opens the sequence, with deep piles driven into stable ground to secure the viaduct's base. Massive pier columns then rise, reinforced and aligned to bear the full weight of 28 spans. It's amazing how those towering piers maintain perfect alignment through every phase. Once both abutments A and B are in place, the deck construction proceeds section by section, guided by tight geometry checks. Next come the pre-stressed concrete beams. Each beam, pre-tensioned with steel tendons, provides unmatched strength against load and vibration. What a sight when those beams are lifted perfectly into place, pure coordination between human skill and machine control. That lift alone captures the essence of precision-driven teamwork. The deck slabs are then positioned and connected, forming the smooth rail-bearing surface. Load testing validates the structure's capacity. Sensors measure deflection and tension as simulated train weights pass across the deck. That moment when the bridge stands firm under the equivalent of a full-speed train is just incredible engineering confidence. The completed 765-meter viaduct now connects 2 major stretches of Italy's evolving rail network, a crucial step toward faster, greener transportation. Over time, it will carry countless trains, each crossing built upon this remarkable foundation of strength and precision. No job on the tracks is too tough for this battery-powered turnout grinder. It is designed specifically for grinding rail joints and switch points. Its lithium-ion system keeps the tool running strong through long field sessions. The tilting setup, up to 50 degrees, handles awkward angles with ease. That tilt range is wild for a portable grinder. Adjustable spacing fits every rail type perfectly. Looks fun to use too. NNN. Numbers tell the scale of ambition here. More than 40,000 kilometers of railways, 30,000 kilometers of highways, and projects spanning 46 countries. This is CRCC, a powerhouse shaping China's infrastructure and reaching across continents with unmatched drive. Railway construction marks its foundation. From the Qinghai-Tibet line cutting through permafrost to the Beijing-Shanghai high-speed route tested at 416 kilometers per hour, every milestone reflects engineering strength. Over 70% of the Qinghai-Tibet route was executed by CRCC teams working through thin air and frozen ground. The line solved three of the toughest problems in world railway history: permafrost, altitude, and fragile ecosystems. No wonder these projects redefine what endurance and innovation can achieve in extreme conditions. Bridge and tunnel construction form another legacy. The Shanghai-Chengdu Arch Bridge stretches 430 meters, while the Kangxi Bridge stands as the world's second largest of its type. Their designs combine rigid frameworks with flexible arches, allowing them to withstand shifting geological forces. Across China, CRCC has completed over 10,000 kilometers of tunnels, including landmark projects like the Qinling Rail Tunnel and Nanning Highway Tunnel. Urban transport expands that expertise further. CRCC helped build nearly every major metro and tramway network in China, exceeding 700 kilometers of urban lines. From Beijing's first subway line to Shanghai's modern monorail, the company has shaped urban travel for decades. Each kilometer built became both a technical challenge and a step toward nationwide connectivity. What ensures every slab track fits perfectly in its final location? The answer lies in careful welding and 3D checks. Welding by certified experts ensures perfect joint strength. Welders adjust alignment dynamically to prevent any future misfits. Painted surfaces dry quickly before the SIAB rotator flips each unit for demolding. Operators verify rotational balance during flipping to avoid damage. Customers verify dimensions in 3D, guaranteeing exact tolerances. Precision like this keeps high-speed trains safely on track. High-speed rail demands not only speed, but reliability and long-term durability. The SlabTrack Austria system rises to these challenges with elastically supported slabs that minimize maintenance and vibration. Prefabricated slabs are produced under strict quality control, with high-grade concrete and integrated elastomeric layers to prevent cracks and reduce structural-borne noise. Slabs are transported directly to the installation site using portal cranes or wagons, eliminating the need for intermediate storage. Accuracy is key. Slabs are positioned with a tolerance of plus or minus 0.5 centimeters, reducing adjustment work drastically. Self-compacting, early-strength concrete secures the slabs quickly, allowing rapid installation during short track closures. Additional fittings, like sound absorbers or guardrails, can be integrated as needed. Damaged slabs can be replaced individually in mere hours, avoiding full section replacement. Ground settlement adjustments are possible through the elastomeric layer. Seeing this system handle precise high-speed rail requirements so efficiently is genuinely impressive. The combination of prefabrication, speed, and reliability ensures safer, faster rail service. The Eppenberg Tunnel stretches kilometers underground, requiring exact alignment over vast distances. Survey crews plot exact alignments, guiding excavation machines through solid granite. Tunnel boring machines cut through layers efficiently, while crews immediately reinforce walls with shotcrete and steel ribs. Drainage channels are installed to prevent water ingress. Ventilation and lighting systems are added, ensuring safe conditions for continuous work. Seeing the coordination between heavy machinery and operators is wild. Everyone knows exactly what the other is doing. Concrete lining sections are poured in sequence, maintaining stability. Safety checks are frequent, minimizing risks. The workflow is smooth yet intense. Crews move fast without compromising quality. Track beds and ancillary installations follow, bringing the tunnel closer to operational readiness. NN